Welcome back to CS103 Machines, Languages and Computation. In this sequence of short lectures, I'm going to finally take us to the proof that there are such things as non-computable functions. We're going to be looking at infinite sets, and what we're going to be trying to do with these infinite sets is map them onto another. So if you remember, we started with the dogs and collars example. We said consider an infinite set of dogs, and each dog has a name which is a finite string of letters, all in uppercase. And what we want to do is we want to take that string of letters and somehow, using an algorithm, map it onto a natural number. The natural number is the collar number. So basically I've got all these collars numbered 0, 1, 2, 3, 4 and so on. And I've got all my dogs, and I want to show that every dog that has a name has a collar, and that every collar can be assigned to a dog. So in other words, there's a one-to-one mapping between the two sets. So what I wanted to do was to actually find this algorithm. And I wanted to find an algorithm that could take me from a dog name to a collar number, and similarly to do it in reverse, to take a collar number and to compute a dog name. And in the end, what we worked out was that we could have a scheme which was a kind of base 26, but with no 0 in it. So if we use a equals 0, that kind of breaks things for the strings, because strings can start with, for example, lots of a's. So Aaron, for example, has 2 a's at the front, and if those were zeros, that wouldn't work. So therefore we have to let a equal to 1. So the way that we do it, in fact, and the way that I worked out how to do this when I first looked at this problem, I said, okay, why don't I just line up all of the dog names in order, shortest first, then so all the dog names with length 0 to start with. There's only one of those. That's the dog with no name. Then I'll have all the strings of length 1, A, B, C, D, E, F, G, all the way up to Z, and I'll number those 1 to 26. So the empty string gets 0, then A to Z gets 1 to 26. Then when I come on to the strings of length 2, I'll start numbering those. That's 27, 28. And after a while, I work out that what's happening here with these strings is that each letter in each place stands for a digit. And A stands for 1, B stands for 2. So AA here, the way that I work it out is it's in base 26. So the first A, that stands for 26, and the other A, that stands for 1. So the whole thing is 27. When I get up to ZZ, each Z here means 26. So A means 1, Z means 26. Now, normally you wouldn't have the digit for 26 in base 26. So that's where this numbering scheme becomes a little strange. But the reason that we have it is it gives an exactly one-to-one mapping. So when I get to ZZ, that's 26 times 26 in that position, and then 26 units. So if I add those up, that comes to 702. The next one is a 3-digit number, and this in this position here, A in this position means 676, in other words 26 squared. So this is 676 plus 26 plus 1, and that comes to 703. And then if you work out this number, ZZZ, where each Z is counting for 26, but this is units, this is 26s, and this is 676s, that comes to 18,278. So I wrote a program and I showed it to you, and it showed you that these sets are the same. That's the concept I want to get through to you. The The numbering scheme that I'm using, it's interesting, but it's nothing that you'll ever want to remember in your working life as a computer scientist. It's just a bit of an oddity, to be honest. But this idea that there are two sets here and they exactly align with each other, that's a really important concept. So I set you an exercise. I don't know if it was exercise 4. These slides are from a previous year, but it was an exercise and I set it to you. Which collar is given to the dog named Odie? Well, what you do is you treat that as a number in base 26. A equals 1, B equals 2, and Z equals 26. And that gives you, well, the letter O, that's the 15th letter. So 15 times 26 to the power 3. This is a number in base 26. So you've got 26 to the power 3, 26 to the power 2, 26 to the power 1, 26s. 15 times 26 to the power 3 plus 4 times 26 to the power 2 plus 9 times 26 plus 5, and that adds up to 266,583. Now, if you don't understand what's going on there, it's possibly because you don't understand how to calculate numbers in different bases. And I'd just recommend that you have a look on YouTube and find a video that explains to you how we can represent numbers in various bases. Now, I also gave you, I asked you what dog gets collar number 106,503. So what you have to do is you have to decode it the other way. What you have to do to start with is you work out how many 26 to the power 3s there are in there. If it's a bigger number, you might have to work out how many 26 to the power 4s are in there, because there's going to be another digit. If it was a 5-character name, then you'd have something times 26 to the power 4 in there. But this is only a 4-character name. So what you work out is that there are 6 lots of 26 to the power 3 in there, and that leaves a remainder. Of that remainder, there's 1 lot of 26 to the power 2 in there. Then of that remainder, there's 14 times 26s in there. And once you subtract that, you get a remainder of 7, and that's the units. So the 6 here, that corresponds to F. The 1 corresponds to A. The 14, that corresponds to N. And the 7, that corresponds to the G. So that's how my program basically does it. It works out what the biggest power of 26 is that's contained in this number, and then it starts subtracting lots of that out and then continues. So hopefully you got that right. And if you didn't, hopefully you understand it now. But the most important point, as I said, these two sets are essentially exactly the same. So the strings and the natural numbers are the same set in essence. Why have I been over that given that such a lot of hot air? Well, what I'm going to do now is I'm going to try and do the same trick on some other sets. I'm going to try mapping them to the natural numbers, and I'm going to run into problems. And because I run into problems, that's going to do a proof for me. So what I'm going to do now is I'm going to move to a different planet, which is probably a good idea. I'm going to move to planet Zog. And on planet Zog, they don't give their dogs names, which are strings. They're different there. On Zog, they give their dogs names of real numbers. So their dogs have names like 0.5 and 3.72 and pi and e and the square root of 2. Come on, square root of 2, time for walkies, that kind of thing. And that's going to lead us on to the idea that there are different types of infinite sets, and in fact, in a certain sense, some infinite sets are bigger than others. And we're then going to look at how big is the set of all the computer programs, and then how big is the set of all the functions that map natural numbers onto natural numbers. And then we'll say, are there more functions than there are programs? And the answer is going to be yes, there are more functions than there are programs, and that means there's non-computable functions. So let's start with these dogs from the planet Zog, and that will get us warmed up with the idea that there are some sets, some infinite sets, which are bigger than others. Let's just say it that way. So these Zog dogs, they have names like 3.58, 15.6, 0.3 recurring, the square root of 2, the square root of 3, pi, e. So any real number, any decimal number, including those numbers which never repeat, the irrational numbers. Any one that you like, any real number. That's a dog from Zog. So there's an infinite set of dogs, just as we had before. And I've got an infinite set of collars. So I've arrived on planet Zog with my infinite set of collars, numbered from 0 upwards. Have I got enough collars for all the dogs? So I'm going to try doing it the way that I proceeded before. I'm going to try to make a mapping. And for that mapping, I'm just going to try mapping from the collar numbers, that's n, that's 0, 1, 2, 3, 4, and I'm only going to do the real numbers in the range 0 up to 1. So I'm only going to try mapping the Zog dogs that have names between 0.0 and 1.0. So that's not even all the Zog dogs, that's only a few of them. If I can't do it for that few, I certainly can't do it for the lot. So the way that I'm going to do this mapping is I'm going to do it on a piece of paper on my desk for you. So I will see you in the next video.